There we go. Okay. Good afternoon, everybody. Oh, that's a bit loud. Yeah, my name's Allan Cantle, and I'm the technical lead for the OCP HPC sub-project. And we've been looking at redefining computing architecture from the ground up. And we've got a particular application. So we've had a concept in the works for a while now, but we were looking at a target application that we could build a POC for. And so the one we came up with was a digital twin ASIC emulation platform using our OCP HPCM Wall of compute, as we call it. So as a quick overview, first of all, like I just said, we're building on the efforts over the last few years of this redefining the computing architecture. There are a number of presentations from the last couple of summits that I'd recommend you take a look at if this interests you, and you'll get a lot more detail. I'll give you a quick overview in a moment. But specifically on ASIC emulation, it's a special type of high-performance compute application that utilizes FPGAs as accelerators for emulating an ASIC before you actually build your own processor chip. And these things have actually been around for decades. And in fact, one of my early companies, we actually did have about 25% of our business from this area. But the demands for ASIC emulation today are actually growing and slightly shifting as well compared to the traditional platforms that you see from the IP providers. And a lot of the silicon startups, VC-backed startups, have been asking for more of an open source emulation platform. So there is a commercial need for this. And so one of the big things, if you follow the hardware, software co-design tracks that OCP has been working on, for evolving AI models, then a big emulation platform where you can emulate a complete chip along with your software gives you a great advantage on getting the hardware right before taping out a very expensive ASIC. This could help towards helping to move towards a chiplet ecosystem. I'll touch on that. And it's really enabling these silicon startups with a better platform. It's a good POC for our wall of compute as well, because it's a fairly simplistic and pragmatic approach for us to do an initial POC. And I'm going to provide details of this in this presentation. So if you've not seen the high-performance compute module concept from our previous presentations, here's a little animation. Basically, this module is roughly slightly bigger than an OAM, OCP accelerator module, but you'll notice that it also has the potential for media to be plugged in. So let me just play this animation. So there's 16 E3.S modules for media in memory to be attached to the module. It's a water-cooled jacket, and inside you see the module that's similar to the OEM. The key difference is this doesn't plug into a motherboard. It's got a bunch of backplane connectors for connecting modules together. If you people are familiar with servers of today with PCI Gen 5, you're probably seeing lots and lots more cables in these servers. It's because the PCBs are no good anymore. We need all these bypass cables. So, and on the back of on the other side of the card, we've got our big, powerful processor, accelerator, GPU, FPGA, AI device, whatever, that may be up to 1 kilowatt of power or more. And so, yeah, this module, this is a universal module where you can put any type of accelerator, heterogeneous accelerator on there, including switches, electrical switches, and even potentially optical switches in the near future. And you can even put your own custom accelerator into this footprint. So this gives us a heterogeneous, high-performance building block. Just putting that back together, it reassembles the water jacket. You'll see as it moves the power pins and the water inlet. And this module then plugs into a wall. So this is one small section of the wall carrying the water and the power, 48 volts, and the module mates into the wall, blind mates into the wall. And then, so now this will move on as well. You will see this module. This is one individual module in one slot of the wall. But here's an example of a small wall with 8 modules tall and 16 modules wide. And you can plug in your modules into that wall, and heterogeneously as well, any mix and match The idea is this is a fully open standard that everybody would comply to. And this would allow you to build any node configurations that have already existed today in any software stacks. So as a couple of examples, the Frontier supercomputer is an EPYC CPU and 4 MI250X GPUs, and there's two of those nodes inside a 1U chassis. We could replicate that with these 10 modules here. And we would replicate the interconnect of that platform by putting the cables to wire these modules together explicitly as Frontiers is done. Or you can convert it to your own domain-specific needs if you have different needs for different bandwidths and feeds between CPUs and GPUs. Another example is we could emulate the Grace Hopper configuration. If you know the Grace Hopper from NVIDIA, they have something like 7 times the PCI bandwidth, or 1 PCI Gen 5 channel between the Grace and the Hopper chip. This, you could cable this together to give you that same bandwidth between 2 modules, a CPU and a GPU module, so you could emulate Grace Hopper. Or if we go back to the older supercomputer Summit with an IBM Power 9 and NVIDIA Volta GPUs, that was a 3-to-1 ratio. In fact, my previous colleague just presented before me was talking about all this modularity. This is exactly what we're doing. We're trying to give you this building block modularity at this granular building block level. If you were building just an AI machine, you can just have a big array of AI devices. If you wanted to build an FPGA disaggregated pool that was optically connected, you could potentially build that. Or Burger King, you can compose it your way. Have any mix of any devices you want. And so that's the idea. This allows us to build our own domain-specific accelerators out of our favorite suppliers, not just the one. Any favorite supplier of the accelerators and processors is a concept here. Get rid of that, sorry. So specifically looking at our use case for this POC, an ASIC emulation digital twin, wall of compute, we're just going to simply build a single FPGA HPCM module based on an FPGA from AMD that is dedicated for ASIC emulation purposes, and then we will tile, we can tile our wall as big as we want with these modules. This is an example of 128 of these modules where you can start to emulate your big ASIC before you tape out. So that's a basic concept. So hopefully that's given you a rough idea of what this module, my previous presentations in OCP Global Summit last year and the Regional Summit this year, will give you a lot more detail if you'd like to understand a bit more detail about it. So why do we need ASIC emulation? So today's largest ASICs are typically accelerators from most people. They're often multiple dies on package, and they typically have HBM at the moment, is very obviously in vogue. But if you look at the structure of these accelerators, largely they're many on-silicon compute tile structure. They have multiple NOCs. There are some heterogeneous elements scattered around on the die, and they have a lot of high-speed I/O as well. NVIDIA Blackwell is obviously a nice example of the extreme of this. The Blackwell chip is 104 billion transistors on the die. They have 2 of those and 8 HBM3Es to go with that. Typically, tape-outs of these types of devices are well in excess of the hundreds of millions of dollars, and I think I have heard Jensen say on one of his keynotes that they're in the billions of dollars a range for them. So you don't want to be doing too many tape-outs. You ideally only want to do one. Hence, the emulation is a critical step in all of this. But simulation and emulation is often used. Simulation is a higher level modeling in software, whereas the emulation is actually more of a faithful representation of the final ASIC, ASIC's logic, and typically it will run around about 100th the speed of the final ASIC. But it's a considerable acceleration over software implementations. So if we look at AMD's latest FPGA that they've built specifically for ASIC emulation, that's their device called the VP1902. It's got 18.5 million system logic cells and 1.1 gigabits of on-chip SRAM. Those system logic cells basically roughly translate to about 4 billion equivalent ASIC transistors in your custom ASIC. They also support 160 transceivers of I/O on this module, split into 128 32 gig transceivers and 32 56 gig. And they can support up to 22 LPDDR4 memory channels. So this is our building block of the device that we're building an HPCM module with. So if we look at that in contrast to the Blackwell, if we're building an emulation platform for Blackwell, we want to emulate this 104 billion transistor die. So that would need about 28 VP1902s to actually build that emulation of that die. Or if you wanted to emulate two of the dies bolted together, you'd need 56 of the FPGAs, roughly speaking. We'd also want to emulate the HBM. And if you're familiar with HBM, actually HBM is constructed of 16 separate memory channels are in one HBM stack. And so what we've decided to do is we use one 2 gigabyte LPDDR4 memory chip per memory channel of HBM that we're emulating. So we'd need 16 LPDDR4 memory channels in 32 gigabytes of capacity to emulate one HBM. So if we look at that now, so there's a block diagram in the bottom left-hand corner, basically of what I just said, the VP1902 with its 160 transceivers and its 16 LPDDR4 memories that can emulate a single HBM stack. And so we could put an array of 64 of these together, let's say, as an example, an 8x8 array, and that would be equivalent to one of those Blackwell packaged parts. So hopefully this is giving you an idea of how you would be able to construct this. And in fact, on the memory front, you could actually emulate a lot more memory channels. So you don't necessarily need to just do HBM. You could model different types of memory structures and more memory-heavy devices with this wall of compute here as well. But this is just the example. So looking at the module itself, this is the HPCM module, as you saw earlier, with the actual FPGA device that we're talking about on it. It's actually it's a multi-chip module itself. It's a very large, very expensive FPGA. But we've got the detail architecture is complete. We've got the on-module BMC architecture is done. We're partnering with Lattice on a completely Libre BMC, an open BMC implementation for management purposes. We've got the memory architecture, basically 8 LPDDR4 packages, each package with 2 LPDDR4 channels in it to give us the 16 that we need. And all the power supply architecture is basically down. So the module is ready to go into its detailed design phase. We are actually, because we've been making so many radical steps on power and thermal management, we are looking at this POC. The FPGA actually doesn't need a kilowatt of power. It needs probably 200 to 400 watts maximum. So we're being a bit more pragmatic and working with partners to demonstrate. One of the big challenges is so radical, people will just say, where do you start? So the POC is all about demonstrating this in a wall of compute fashion, and then with a real application, and the FPGA isn't quite as demanding as a kilowatt NVIDIA processor versus like I said, we're about 200 to 400 watts. And also on the universal topology interconnect, which is another feature of this approach, we're working with several interconnect companies. We only need to handle 112 gig speeds, not the 224 yet in this. So again, we're trying to simply be pragmatic with our POC. And we've been working diligently. In fact, this week I'm busy with all the colleagues, all the partners, on putting a POC proposal together to try and get some funding from the DOE New Frontiers RFP, which is an R&D for next-gen supercomputers. So we're hopeful that we can get some funding to actually turn this POC into a reality. So just to look at a little bit more, at the chassis level, I showed you the idea that your infrastructure would be, you'd have walls. There are no 19-inch racks anymore. We just have walls. The infrastructure builds walls, and we have thousands of modules being populated on those walls, depending on the size of your system. But from a pragmatic perspective, there is a company, and I'm going to ruin the name of them. I call them Corno, but there's a much better, clear name. They are in the downstairs area. You can see this box. in the downstairs area, they effectively have a water-cooled wall already where they cool, you can see in the picture on the middle here, they're cooling 3 OCP blades here. So they actually firmly mount that chassis to a water-cooled cold plate, and that's how they cool those servers. And they've got, basically they have 12 of those blades inside this chassis. We're going to, they're going to redesign this to support 36 or maybe a few less of our HPCM modules inside this. So we'll have like a mini wall inside this chassis. They are already in production. They use this in Europe for heat reuse purposes, where they feed a heat network, heating swimming pools or offices in homes, etc. And so this will give us a nice chassis platform to just demonstrate it without having to build a physical infrastructure wall. Again, a pragmatic approach here. And one of the other things, if you've been involved with OCP and the open chiplet economy, what used to be called ODSA, we've been working on chiplets for a long time, and we really want to get chiplets to an industry standard. And there's a chance here to actually help the enablement of the chiplet community. And so with regards to this, you can use this emulation platform, and third-party providers of chiplets will give you an emulation IP that you can put in your entire emulation design. But there's a potential opportunity when chiplets already physically exist and you haven't taped out your chip yet, you could actually build custom HPCM modules with an FPGA, with chiplet interface, where you bring real chiplets into your emulation platform. I call that hardware in the loop. You're bringing the real chiplets you're going to use in your end ASIC device, in your end package, into the emulation, so you can get over any issues between the differences between their emulation implementation and their real physical chiplet. So this is an opportunity as helping in chiplet enablement as well with this approach. So in summary, we've identified an application to showcase our HPCM wall of compute that we've been conceptualizing for a few years now. It's a scalable ASIC emulation platform based on the FPGA HPCM modules. We have growing interest from VC-backed silicon accelerator companies. Basically, I've spoken to 3 well-backed VC-backed ASIC accelerator companies, and all of them love the idea of this, and they're fed up with the current systems just do not suit their needs for various reasons. So there would be a market pool for this POC. We are taking this pragmatic approach, like I said, for not losing, but trying not to lose the HPCM's original vision and intent, so people can really see how this concept can be realized. So we're leveraging existing technologies from other OCP members, truly in an open community here. There's multiple participants in this proposal, and we're trying to deliver a cost-effective product in a faster time to market. So we have this, and finally we have this opportunity to be an essential ingredient in the evolving chiplet ecosystem. So my main call to action is, hey, if this excites you from whatever angle, you're a system architect, a silicon startup, and your VCs, or you're just interested in FPGA acceleration, come along and join our work group. It's the OCP HPC subproject, and help us execute on the vision of this HPCM wall of compute. Okay, thanks very much.
We have time for 1 or 2 questions. Yeah. Can you speak nearer to the mic? Thank you.
In that wall of compute, are you passing through the liquid all the way through each one of those modules in and out?
Yeah, that's so in the full implementation, the water it's a blind mate water and blind mate power for every module.
Yes.
So water flows into the module. It flows into that manifold at the back that you saw, that orange piece, where the E3 drives plug in. So we conductively cool the E3 drives into that manifold. So the veins between all the drives carry water through. So that cools the drives first conductively. There's no air cooling at all in this. Then the water is passed back up onto the other side where the processor is, a kilowatt processor, And that can either be a mini immersion cooled chamber. So we're looking at two-phase options, and this is where it gets really radical. And for pragmatic purposes, we're not going there. But you can either have a traditional water-cooled plate put on top of the processor or immersion cooled. So we're talking to various people on that. And then the water flows back down. Once it's gone across the kilowatt processor, it goes back down to the manifold and out of the other blind mate interconnect. So the water gets kind of.
What is the size of that module? I mean,
It's a little bit bigger, including the thermal jacket. It's 200 millimeters by about 120,
okay.
or 6 inches, or 6 or so inches by 7 or 8 inches. Okay.
Okay. Thank you, Allan.
Thank you.